This is going to be a quick and easy basic lesson on molarity. Now, molarity is a measurement in chemistry of a solution, and we're going to understand this or learn this by going backwards. So we're starting at the end and we're going to move backward because you have to know a few fundamental things in order to understand molarity. So first off, like we said, molarity is a measurement of a solution. If you remember, a solution is made of two parts. So here I have a cup, and in this cup there is water. Now the water is my solvent. All right, the solvent is what does the dissolving. It dissolves the other substance, which is the solute. All right, so within this water, we have dissolved substances, and let's say this solute is sugar. So a solution then is a solvent with a dissolved solute within it. And if we want to measure how much of the solute is in the solvent, that would then give us what's called a concentration. So the concentration equals the amount of solute divided by the amount of solvent. So specifically, molarity, which as we just mentioned before is a type of concentration, is going to equal a measurement of solute called moles. So this is the moles of our solute divided by the liters of solution. Now, as we said before, a solution is both the solvent and the solute. And that's how we're going to calculate molarity. Well, now we're going to have to go back from here because what's a mole, right? A mole is another measurement in particles, or in this instance, the number of sugar molecules. All right, so a mole is the number of atoms, particles, molecules, could be any of those things, equal to the number of atoms in 12 grams of carbon. All right, now that's maybe doesn't help you too much, but we actually know how many number of atoms there are in 12 grams of carbon, and that equals 6.022 times 10 to the 23rd atoms. All right, but that's in 12 grams of carbon. But this could also apply to particles or molecules, which are slightly different than atoms. All right, this is called Avogadro's number. Avogadro was the scientist who came up with this unit of measurement. And this allows us to make then solutions based on this concentration, which accounts for the number of molecules, whereas grams and other things um, don't, right? Grams and volume and liters, those are how much space or how much mass they're taking up or how much matter is there, but it's not taking into account the actual number. All right, well, this is going to be a little bit difficult because we can't just count the atoms. So to help us with that, we have the periodic table of elements. On the periodic table of elements, these are organized in a specific way, but also generally you will find a number down here. This is called the atomic mass. And the atomic mass is actually the same as the molecules in 1 mole. So that's to say that 1 mole of boron is equal to 6.022 times 10 to the 23rd atoms, and that 10.81 grams of boron also equals 6.022 times 10 to the 23rd atoms. All right, so we know then that 1 mole of boron equals 10.81 grams. And this has been determined by chemists, and I don't exactly know how. But that's not important for the calculations we're going to make. All right, so this is simple enough if you're talking about just one specific atom. But let's say you are interested in knowing a molecule, something that has more than one atoms in it. Well, let's talk about a very simple molecule compound that we are very familiar with, which is water, which, as we know, has 1 oxygen, okay, and 2 hydrogens on it. So the red is hydrogen, the blue is oxygen, and that makes up a molecule of water. If we wanted to know, well, what's 1 mole of water? How much mass is that? Okay, we just need to add up the molecular weights of each of the individual atoms in that molecule. So that's going to equal the atomic weight of oxygen, which is 16, plus 2 of the atomic weight of hydrogen, which is, we're going to round to 1.01. And that then equals 18.02 grams. So there are, in 18.20 grams of water, there are 6.022 times 10 to the 23rd atoms, and that equals 1 mole. All right, so let's talk about then how we use that to measure molarity. As we mentioned before, molarity equals the number of moles divided by the liters per liter, 1 liter of solution. So let's say we have 10 grams of boron in 2 liters of solution. So after we add the 10 grams to water, it equals 2 liters. What's the molarity? Well, the simple calculation, we have to do 10 grams times however many grams per mole that equals. And we're going to have to go back to our periodic table of elements to discover that. And if you remember, our periodic table had boron, right? And it had the number 10.81 below it. And so that is the number of grams in 1 mole. And so if we want to determine how many moles are in this liter, we need to convert that into moles. So we know 10.81 grams is in 1 mole. And so we just need to divide then 10 by 10.81. And we're going to get something close to 1, which is 0.925. And then the symbol for molarity is a capital M. And we would say that this solution is 0.925 molar. All right. So one other example, let's say we have a 0.5 molar solution of boron, and we have 25 liters of water. And we want to know, well, how many grams of boron do we have? All right, well, we know this 0.5 molar solution equals 0.5 moles per liter. And we have 25 liters of water. And we want to also know the grams. So we know 1 mole of boron is 10.81 grams. So when we do this, we can figure out, we can cancel our moles here and cancel our liters there. So 0.5 times 25 times 10.81 gives us the number of grams in that solution. And that's going to equal 135.125 grams of boron. So there's a lot of different calculations you can do when you have this information. But let's just review then. Molarity is a measurement of moles per liter of solution. A mole is 6.022 times 10 to the 23rd molecules or atoms. And the molecular weight found on our periodic table of elements equals how many grams that are in 1 mole of that substance. Now, one other thing to note, you may see me write an E or sometimes just not have the E on it. Both notations are acceptable in chemistry, so you'll see both of those. All right, so now when you see different molar concentrations, you should be able to understand what we're talking about.